Hey everyone, and welcome back to The Explainer. Today, we're diving into something really special. We're uncovering the fascinating and honestly pretty wild human drama behind one of mathematics' most famous theorems. We're going to blend the pure, perfect world of geometry with the highly imperfect and sometimes chaotic human beings who actually pushed it forward. Let's get right into it.
Okay, let me ask you a quick question. What on earth do stolen ideas, literal blindness, and right-angled triangles all have in common? I know, it sounds like the setup to a strange joke or a crazy movie plot, but to truly understand the math we use today, the exact same math used to build suspension bridges, launch satellites into orbit, and safely chart the oceans, we first need to meet the scandalous masterminds who pushed those mathematical boundaries to the absolute limit.
So there is this incredibly stark contrast between two absolute titans of early modern mathematics. On one side, we have Leonhard Euler. This man, he was arguably the greatest mathematician of his entire generation. He didn't just casually study math on the weekends, he completely revolutionized it. And here's the wildest part. Even after tragically losing his sight and going completely blind, Euler just kept going. He continued to produce absolutely masterful work. He proved the sum of the infinite series, he heavily advanced calculus, and he introduced the constant symbols that we literally still use every single day. Things like pi, the letter e, and I for the square root of -1. That was all him. But then, on the other side of things, you have the Bernoulli family. Now, they were brilliantly gifted Swiss merchants and scientists, and they were actually friends with Euler. Brothers Johann and Jacob, along with their kids and grandkids, made these massive leaps in calculus, probability, and mechanics. But here's the catch, and it's a big one. They were notoriously toxic. I'm talking deeply, deeply jealous of each other's successes. The older Bernoullis were so petty that they literally stole mathematical work from their own sons and grandsons and then published it as their own just to steal the glory. Can you imagine?
Now, despite their absolutely terrible family dynamics and, the blatant intellectual theft, the Bernoullis, alongside Euler, made incredible scientific discoveries. The foundational work they laid in thermodynamics, mechanics, and astronomy ultimately helped us calculate complex planetary orbits, map out the heavens, and navigate the stars. Their mathematical obsessions, however flawed the men were in their personal lives, essentially built the framework for the geometric rules we rely on to understand the universe.
But here's the thing. To do all of their advanced, world-changing work, Euler and the Bernoullis had to rely on much older, ancient foundations. And none of those foundations is more famous than Pythagoras' theorem. Long before these modern scientists were looking up at the stars, the ancients established this specific, unbreakable relationship between the lengths of the three sides of a right-angled triangle. You probably remember it. It's beautifully simple. A squared equals b squared plus c squared. But have you ever stopped to wonder, why does this actually work?
Well, rather than just memorizing this equation like a textbook robot, let's do something better. Let's look at how mathematicians visually prove that it actually physically works. Because let's be real, seeing is believing. And in geometry, transforming an abstract algebraic equation into a physical, visual puzzle is hands down the absolute best way to lock it into your memory forever.
Let's break this down step by step, because it brilliantly illustrates exactly how the magic happens. Imagine, in your hands, taking 4 identical or congruent right-angled triangles. Each one has a long side, we'll call that A, and 2 shorter sides, B and C. Now, if we rotate them around and piece them together like a jigsaw, they form a perfect large square. And the outer boundary of that square is made up entirely of the side A. This means the total area of this big outer square is just A squared. Simple enough, right? But look at the center of our puzzle. By piecing those triangles together, there's a little square hole left over right in the middle. The length of the sides of that little hole is exactly b minus c, which means its area is b minus c squared. Now, if we take the area of that little central hole and add it to the area of our 4 identical triangles, the algebra beautifully expands and simplifies right down to a squared equals b squared plus c squared. Just by arranging 4 triangles into a square, the math proves the theorem right before our eyes. It is elegant, it's undeniable, and honestly, it is a pure geometric truth.
Okay, so now that we know the proof is rock solid, and we've literally seen how the geometry fits together perfectly, we need to ask the practical question: how do we actually use this? If we are given an incomplete puzzle in the real world, how do we apply this exact equation to find the lengths of unknown sides?
It's really just a bit of algebraic gymnastics. Notice how we just rearrange the exact same formula depending on whether we need to find that long diagonal side, the hypotenuse, or one of the shorter straight legs. Let's say we want to find the longest side. Let's call it A. We simply add the squares of the other two sides. For example, if our two short sides are 8 meters and 6 meters, we just square them to get 64 plus 36. That equals 100. And what's the square root of 100? It's 10. Super easy. But what if we already know the longest side is 12, and one of the short sides is 5? Well, we just have to work backwards. We subtract. So 12 squared is 144, 5 squared is 25. 144 minus 25 gives us 119. So that missing short side is simply the square root of 119. It's the exact same master key. You're just turning it in a slightly different direction to unlock the piece you need.
Now let's see how this builds into an incredibly practical tool for testing reality itself. Because what happens if you were staring at a triangle, maybe it's drafted on a blueprint for a house or surveyed out on a plot of land, but you aren't absolutely 100% sure it has a true perfect 90-degree corner? You can't just trust your eyes. Human eyes are easily deceived. A line that is 89 degrees looks virtually identical to one that is 90 degrees. To solve this exact problem, we can use what's called the converse of the theorem to mathematically interrogate the shape. Basically, we use the theorem backwards to test reality. This ensures we never, ever blindly assume a triangle is right-angled just because the sketch makes it look like one. Think about it. If the triangle truly has a perfect right angle, it absolutely must satisfy the equation. If it fails the equation, well, the right angle is a lie.
Let's actually put this into practice and test a specific triangle right now. Imagine we have a geometric plot and the sides measure exactly 6 centimeters, 7 centimeters, and 9 centimeters. We're going to plug those numbers into our geometric test. First, our longest side squared is 9 squared, which gives us 81. Okay, keep that number in mind. Next, we check the sum of the squares of our two shorter sides. 6 squared is 36, and 7 squared is 49. When we add 36 and 49 together, we get 85.
Well, I certainly don't need to tell you this, but 81 absolutely does not equal 85.
And because those numbers don't match up, we have absolute, mathematically undeniable proof that our suspected triangle does not contain a right angle. No matter how perfectly drafted it looks on the page, the math simply doesn't lie. It failed the converse test. This is just an incredibly powerful diagnostic tool. You can essentially audit the structural geometry of any building or plot of land just by measuring its three sides.
And far beyond the chalkboard, these exact right-angled calculations are used every single day out in the real world to navigate, build, and sometimes even survive. For example, if a village in the Namib Desert is 30 kilometers due north of you and another is 65 kilometers due east, Pythagoras tells you the exact shortest diagonal distance across the sand. No guessing required. Or think about maritime navigation. If two boats leave a port at the exact same time, but they travel on entirely different compass bearings, say one's heading out at 325 degrees and the other at 235 degrees, their paths form an angle. By mapping their speeds and tracking their time on the water, Pythagoras' theorem allows us to calculate the exact distance of open ocean between those two vessels at any given moment. It's also exactly how land surveyors map the shortest perpendicular route from a single point directly to a continuous road or a boundary line. It's everywhere.
So the next time you need to find the most direct path from point A to point B, or you're just looking at a corner trying to figure out if it's perfectly square, I want you to remember all of this. Remember the brilliant blind Euler pushing through his struggles. Remember the wildly jealous Bernoulli family fighting over credit. And most importantly, remember the elegant, ancient power of the right-angled triangle. Mathematics isn't just numbers in a book, it's a living toolkit built by brilliant, flawed people to help us make sense of the physical world around us. So how will you use this geometric puzzle to map out your own challenges? Thank you so much for joining me on this explainer. Keep learning, keep questioning, and I'll catch you next time.